Hey Adventers, welcome to day 11 of Advent of Code 2024. Today we are presenting from a hendecagon camera, which is also called an undecagon camera because 11 sides for 11 days. And here's a question for you. When do you think my face cam will start to resemble a complete circle? I think by the time it's day 22, because I'm stuck in the bottom right corner of your screen, probably the 22 side polygon would be indistinguishable from a circle. But yeah, before we start, in case you are new here, welcome. I'm Jatin. I'm a principal engineer who absolutely loves solving these problems. And if you haven't check out my day 1 to day 10 problem solving series where we have a spoiler free discussion in how to approach the problem. And it's very useful in case you are new to programming or you want to master the art of how to solve a problem before writing a single line of code. And with that, let's get started with our day 11. It's fairly cold today in Chicago. It's close to minus 10 and probably it's going to start to snow again. But that doesn't affect our spirit of Christmas and problem solving. So let's get started and let's take a look at day 11. So day 11 is called Plutonian Pebbles. Let's read it. The ancient civilization on Pluto, and this is a reference to 2019 day 20, was known for its ability to manipulate space-time, and while the historians explore their infinite corridors, you have noticed a strange set of physics-defying stones. At first glance, they seem like normal stones and they are arranged in a perfectly straight line. So they are always in a straight line. And each stone has a number engraved to it. So basically, each stone has some kind of a number engraved to it. Number, ID, I think number is a easier word. And the strange part is that every time you blink, the stones change. That's interesting. Let's see what it means. So it says that sometimes the number engraved on a stone changes. Other time a stone might split into two, causing all the other stones to shift over a bit to make room in their perfectly straight line. So I think this is the second time they have referred that the stone will always be in a straight line. And whenever there is a number change or it gets split into two, it will cause all the stones to shift over a bit. And as you observe them for a while, you find that the stones have a consistent behavior. Every time you blink, the stones each simultaneously change according to the first applicable rule in this list. So we are given some rules and they follow an order of precedence in the order they are given. So the first rule says that if a stone is engraved with number 0, so if you have a stone here and it is engraved with number 0, as soon as you blink, it is replaced by a stone that is engraved by a number 1. So it's essentially like flipping a bit. So we are reading the rules from here. So this was our first rule. The second rule says that if a stone is engraved with a number that has an even number of digits, it is replaced by 2 stones. The left half of the digits are engraved on the new left stone, and simultaneously the right half of the digits are engraved on the right stone. The new numbers don't keep extra leading zeros, which means let's say if it is 1000, it will become stones like stones of 10 and 0. So very interesting. So remember, it's not saying an even number, but it is saying the even number of digits. So if you have a stone here, which has, let's say 44, once you blink, it will basically become 2 stones of 4 and 4 each. And let's take a bigger example. Let's say you have 1205. As soon as you blink, it will become 12 and 5. So basically, it is always being split from the middle, split into halves. And since it's an even number, you can perfectly split it into 2 numbers from the middle. And the third condition, I think that probably is going to be the catch-all condition here. It says that if none of the rules apply, the stone is replaced by a new stone and the old stone number is multiplied by 2024 and is engraved on the new stone. So for example, if it is neither 0 or neither a even digit of numbers, so let's say if we have a stone that has number 100, which is neither 0 nor even number of digits, on a blink of an eye, we are going to multiply it with 2024. So this will become 202400, which is 202,400. And we will engrave this on a new stone. So there will be no split in the third rule. And it says that no matter how stone changes, their order is always preserved and they stay on their perfectly straight line. So I think that's the fourth time they are referring to it, probably something to keep in mind. And what we have to see is now that how will the stones evolve if you keep blinking at them. You take a note of the numbers engraved on each stone in a line. That is our puzzle input. And there is an example given to us. So let's check that. I will make some space here. And it says that we are given an arrangement of 5 stones engraved with the following numbers. So we have 0, we have 1, we have 10, we have 99, and we have 999. So this is basically T0. On T1, when you blink once, let's see, and let's try to do this without directly looking at the answer, and let's look at the rules. So if a stone has 0, we replace it by 1. So this 0 becomes 1. And if a stone is 1, but it's not an even number, it will be get multiplied by 2024. So this 1 into 2024 would be 2024. If you have a 10, which is a number with even number of digits, we will split it into 2 stones. And since we are not keeping leading zeros, this will become 0 and 0. So 0 will still have some validity. So this will get split into 2 stones. So this is like this is like this gets split. 99 is again even number of digits. So we will split it into 2. So 9 and 9. And 999 is 3 number of digits. So we will multiply 999 with 2024. So let me do that. It's 2021976. I did a quick calculation. So 2021976. Is that correct? 2021976. Perfect. And this is basically the result after we blink once. That's all. And if you see, like, we are maintaining the order of stones. And even if you split, it basically just makes space for the new stones by shifting all the elements ahead of it. And that's not a hint, but you can think of like some data structures that makes it much easier to do that than others. So after blinking, this is the new arrangement: 1, 2024, 1099, and 2021976. And then there is another longer example where they have started with 125 and 17. And I think they're following the same set of rules here. And I'm not going to do this, but what you should do is you should definitely do a dry run of this example here just to understand the question better. But if you look at the first one, this doesn't fit the rule 1 or rule 2, so we multiply it by 2024. And then the second one follows the rule 2, so we split the 17 into 1 and 7, and then so on. And after 6 blinks, we get some number. So in this example, after blinking 6 times, you would have 22 stones. So, okay, so we are basically counting the number of stones after n blinks, right? So here, if you see, like, after 1 blink, we had 1, 2, 3, 4, 5, 6, 7. So we had 7 stones. And in this case, I think they're saying that you will have 22 stones. And after blinking 25 times, you will have 55,312 stones. So now the question says that consider the arrangement of stones in front of you. How many stones will you have after blinking 25 times? And we are given this puzzle input, which is very small. We initially start with 1, 2, 3, 4, 5, 6, 7, 8 stones. But we can see that this probably will grow really quickly. And I think now is a good time for you to pause here, this video, and think about the problem. Probably try to dry run this 6 times to get an idea and think about how you will solve this problem. So grab a pen, paper, a notepad, whiteboard, something, and try to just write down the rules and try it out with a couple of test cases. And then once you are back, we will discuss some strategies of solving this using some code. Okay, so if you're still here looking for hints, let's start. I think we have only two things that are very interesting in this question. A, we have to find a way to do these transformations while maintaining the order of sequence of stones so that we don't disrupt them. And second is, how do we store these arrangements in such a way that we do not run out of memory? So it has to be memory efficient or time, because we just don't want to keep our program running forever, because this can turn into a lot of calculations. And I think one more interesting point to consider here is, like, what is the operation that is most costly? That is very costly. So if you look here in the rules that are given to us, the first rule is very simple, where if there is a stone with 0, you just replace the number with 1. And in the second one, it is also relatively simple, where if there is anything that is even number of digits, you just replace it with 2 stones. But this is costly, especially if you are using a traditional array, because every time when you will do a split, you will need to transfer over all the elements ahead. And in the worst case scenario, if your first stone is 2 digits, it will have a complexity of on at every blink. Like whenever you blink, if there is some some even digit number in front of the array, you will basically have to transform the array and move everything ahead. So I think that that is a good enough hint for you to think about what we will use. And if you still don't get it, 2 words: linked list. Exactly. Because in a linked list, since you have nodes connecting and pointing to each other, whenever you have to insert a new node, let's say in this example, and 0, so this 1 will become 2024, and this 11 will split into 2. So all you need to do is you need to keep 1, update this as 1, and take a new node, point that to 1, and point the last one 0, that becomes 1, to this node. And that takes care of your both memory and time. Time, because it is very quick. Instead of updating a whole array in memory, you're basically just updating one node that is pointing to the next node. And if you see the third operation, that is also fairly simple, because we are just taking a number and we are multiplying it by 2024, which is an arithmetic operation that we can do it in constant of one time. So with that, I think you have everything you need to write some code for this. So by representing the initial list in a linked list and then iterating over the linked list probably 25 times, we should be able to get our answer fairly quickly. So I will go ahead and write some code to get the answer for the part 1, and I suggest you do the same. Hey, we're back, and as you can see, we got the right answer and we got the gold star. And I did not do anything crazy here. I followed the same thing. Interestingly, I follow both the initial brute force, where since I'm using Python, I can always just do the .extend function call on my list. It is a little costly, but surprisingly, I also used a linked list approach using the inbuilt DQ library. And for 25 blinks, surprisingly, in the runtime, I ran a benchmark. I'll probably post it here. I did not see any difference. They were fairly close within the margin of error to each other. And interestingly, when we started in our puzzle input, we started with 8 stones, but just after 25 blinks following these 3 rules, the final answer that I got was over 200k just in 25 blinks, which means it is the input was growing, the output was growing really fast, but not fast enough to make a difference between both of these approaches. But with that, let's go and see the part 2. And oh, interesting. Oh, the part 2 is here, and it's basically just 2 lines. I'm going to hide this answer. And the part 2 says that historians sure are taking a long time. Here it took us like 0.12 seconds on my octa-core machine. But to be fair, the infinite corridors are very large. How many stones would you have after blinking a total number of 75 times? Okay, I see where it is going. So, see, this is why exponential calculations are fun, because they grow like this. So, at a small scale, an exponential function can mimic like a very linear behavior. But then the output or the sample space starts increasing so high that probably when we reach like 75, the number is going to be very, very large. And I'm just predicting that. And let's think about the problem though. So now it is saying that we just have to run this like 50 more times after 25. And that will probably increase. If we look at the order of growth from 8 to 225, I think if we keep growing in the same order, where will we land? Probably I'll run out of my RAM, my hard disk, like every possible space in my computer. So how do we approach it? Yeah, I'm going to still try doing the both brute force and linked list approach here, but I am fairly sure that it is not going to work. So let's think, looking at this problem and how the input is growing, I'm going to put this back to this example that was given to us just to analyze like what we can do. So one of the interesting concepts that comes to my mind, I think immediately, like whenever I see some such problems where our samples number and sample space is growing huge, is either to see if we can do like a divide and conquer approach. And the second approach is like, how can we make it less compute intensive? And usually the answer for that is memoization. So this is probably a hint where I'm just looking at the discussions we are having. And the most costly operation that I can see here was this split operation that was happening. And I can imagine that it will, for a number, once you multiply it with 24 here, and once you start splitting it, it will probably split in multiple spaces. And then over the course of period, whenever that large number becomes like a odd number, it will again be multiplied with 2024 here and then will become like really large number. And then that will happen. But looking at this example that was given to us here, so we start with, let's take a different color. So we start with 125 and 17. And in terms of divide and conquer, I just want to see if I can just. So again, in divide and conquer, there are multiple ways. I think one way is that we can split the workload by using like some kind of different threads here. And if we don't use like threads, we can also think in terms of context. Can we calculate things individually? And if we do that individually, we can see that 125 becomes 253,000. And 17 becomes 1 and 7. And now that we had 2 stones here, now we have 3 stones. So I'm thinking, can we again divide this and target them differently? So in this case, this becomes 2530. This 1 becomes 2024. And this 7 becomes 14,168 because it got multiplied by 2024. And now we have total number of 4 stones. And again, following the same approach, we can just keep tackling each number individually. So 253 is falls into the third bucket. It becomes 512072. The 0 becomes 1. 2024 becomes 20 and 24 because it falls in the second bucket, 4 digits. And 14168, see the one I was talking about, it has odd number of digits. So we'll probably multiply this with 2024, which comes to 286,76032. And if you see this, this is like 28,676,000. So the magnitude of number is really high. And 1, 2, 3, 4, 5. So we are at 5. And again, if we keep doing this, one interesting pattern I can observe in this problem is that at the end, all we care about is the total number of stones. But looking at this question, do we really care about the order here? Like all we care about is ensuring that the number that is assigned to a stone counts as like 1 stone. And we don't lose a track of that. Which makes me think that instead of doing this and putting this in an array and solving it like for multiple times, what we can do is we can just solve for, while starting, we can start differently for both of them. And then we can come up and this immediately makes me think of like a recursion use case. But definitely with memoization, while we don't see a repetition here, I have a feeling that for a very large input, we will definitely see some numbers again. Actually, we can see them. We can see them here. I think I'm not going to keep writing it, but if we come here on the right side, I'm going to put like a box here. If you see that we have 2024 number here, and then after two blinks, we again get a 2024 number here. And similarly, we get a 20 and 24 here, we get a 20 and 24 here. And we can see a lot of repetitions. I think this is a good hint. So you can see 4048, 4048, 4048. So looking at this, if I can maintain like a map or a cache of these calculations to say like what comes after this, till you write something to probably the number of stones, that will really help me find the number, because then I can do divide and conquer, do a recursion, have a simple calculate method where we pass something and then maybe use like some kind of this cache to do an early exit. So like if in cache, you just return the value instead of going down the line again and again and again. And this might help us calculate the scope of the problem very less, because now I don't have to worry about storing the whole array and altering the array and maintaining the order. And that's a theory. And I think the best way to try theory is to write some code. So I think I'm going to do that. But just for the kicks, I'm going to first run the brute force and the linked list method. I have a feeling it will not even compile, like we will not see any result. But then I'm going to try like a divide and conquer approach with some memoization to see how that helps us. And one interesting thing here, I think the observation that we made is that the order of the stones initially when you are taking a calculation, it doesn't really matter here, because even if we would have started with 17 and 125, it would still basically be restricted to a stone where you will get the same numbers and then you will keep increasing them and so on. So yeah, probably now is a good time for you to also write some code, and I'm also going to do that. And I will see you in a bit. Hey, we are back, and as you can see, we finally got one gold star. I'm not gonna lie, this was like probably the first problem where the brute force did not work, because till now from day 1 to day 10, like if you had a decent enough laptop, you could have just brute force your way through the problems. But this one was really, really interesting. The sample space, if you kept simulating, would become so large. I probably will link some fact here from a subreddit, Advent of Code. But yeah, I think I tried doing the brute force, and I have a pretty new PC with like 16 logical cores and 32 gigabytes of RAM, and it quickly just started filling up the space, and I was barely at 40th blink. And remember, like it took me a fraction of second to go from 0 to 25, but going from 25 to 40, it took like 5 minutes. And I got tired after that. And in meanwhile, I was just writing my code with the cache and by calculations. And I followed the exact same approach. The only one thing that I changed is, like while storing results in cache, I just put like a cache on top of the function instead of putting a cache over the whole sequence, which is incorrect and will take up a lot of memories. Because remember, I think we are only doing 75 blinks and you will have only 75 sequences, but that's not what we should be caching. We should instead be caching the stone result at each value, right? So the function that where you are writing your 3 if statements, where there is if 0, then 1, and if even digits, then do a split. And then else, like if nothing happens, you just multiply it with 2024. I think you need to put like a cache on this, which helps because then next time, whenever you see the same stone, you don't bother going into this loop and doing all of this. You can just take the value, return it from there, and you can just keep going. And at the end, when you're calling your calculate function, so I used recursion and I hit calculate in a loop for each stone. And at the end, when you get like an output, you basically just do like a total plus is equal to like whatever the value you get from here. And then this becomes your final answer. And in case you are still confused, what I'll do is I'll push my code to GitHub, and you can find the link below. And I will try to document it really well with a couple of examples and test cases on how the method works and how it expands. And for shit and giggles, I will also just put the benchmarking framework, I think, in the main function. So you can run it yourself and see the difference between both the approach and how much difference it can make when you think of a problem in a different way. And this is very close to some of the production problems that you may face as you grow as a software engineer in your career. Because a lot of times the brute force is probably the way to go. But sometimes like doing some minor optimizations can result in like a 10,000x improvement in the runtime of your code and make the whole service very efficient. And with that, we are at end of our day 11. If you go back to the advent of code, I think I was right in the last video. This probably is going to become a 10 here, and it has starting to resemble that. And I guess it's because it's the 10th year of advent of code that we have been solving these puzzles. But yeah, that's it for the day 11. And let me know in the comments below if you have any feedback or any suggestions on how I can make these videos better to explain some of the things. And if you like this, please subscribe to my channel so that you don't miss any of the future. How many days are left? Like 14 more days of videos. And yeah, share it with your engineering and non-engineering friends as well if they are into problem solving. And with that, I'll take your leave and I will see you again on day 12. Bye-bye.